this is my Lab 4 presentation for spring oscillation for Physics 2211. So to start off this lab, our goal is to create a model predicting the movement of an object on the end of an oscillating spring, which will be moving in an elliptical shape. And this is calculated by using graphs of motion and the change in energy, supported by Newton's second law of motion, and is based off gravitational potential energy, spring potential energy, and change in kinetic energy. So some basic physics principles for the energy principle formula: change in energy must always equal 0, because energy must be conserved and cannot be wasted. So change in kinetic energy plus change in gravitational potential energy plus change in spring potential energy should always equal 0. And the formulas to find the three values previously stated is right here. And the momentum principle, which we used for our past couple of labs, is net force equals change in momentum over change in time. And force gravity and net force is listed right below. Net force, our formula we're going to be using is the spring force plus gravitational force, because those are the only two affecting the object. And these two equations on the bottom for the relaxed length of the spring and K, these are going to be used for the spring formula, which we implement our own values into. So for the GLOWSCRIPT code, we start off with the basic. I use the default video, so the mass was 0.402 kilograms, and the position of the ball or the object was found in the tracker, which is listed right here. So using the formula in the last slide, we calculated the spring constant by using time, using the change in time, and then by using the spring constant, we found the relaxed length of the spring, which is listed right here. So by editing these next few lines used for the spring formula, we were able to find S, L hat, and L, which are all the values needed, which are then used to find the spring potential energy. And gravitational potential energy, kinetic energy, and total energy are found right here, all found on the last slide. So then I implemented the time found in the tracker, almost 10 seconds, to find the initial energies, and correctly calculated the spring force and gravitational force. And by adding these together, you were able to get the net force, which is then used for the velocity and position update method. And then we have to update the springs and finally calculate the last energy changes. And delta E is the energy minus the initial energy, which should always be 0. So here's some observations in our tracker. Play the video. You can see the spring is swinging back and forth in an oval-like motion. And our goal is to make this model look the exact same, so let's play it. All right, while it is a bit slower, it is in general the same shape, so let's continue. So some graph observations, we can see that gravitational potential energy, spring potential energy, and kinetic energy are all listed as green, red, and blue, and change in energy is orange, which should always be 0, which is correct. So what does it mean? Is the energy principle satisfied? And yes, as you can see in the last slide, the orange line maintained itself at 0, showing that energy is always conserved, meaning the model is correct. And looking at the oscillation of the graph, we're trying to find the period of oscillation between the x and y coordinate. So in the x coordinate, it is 1.662 seconds, and in the y coordinate, it is 1.496 seconds. Thank you for watching.